This is a pre-recorded presentation for the 21st International Symposium on Aviation Psychology, titled "The Customer is Always Right: Towards Rhino Pointing and Eye Tracking Interfaces for Combat Aviators," presented by Patrick Highland, authored by Patrick Highland, Daniel Harp, Thomas Schnell, Eric Geiselman, and Paul Havig. At warfighter request, research was conducted to determine the military utility of eye tracking as a human-machine interface for large area displays in a tactical live flight environment. Flight tests determined eye tracking felt effortless until rapidly changing lighting conditions and pupil sizes, as well as elevated gravitational load factor induced eye tracker slippage, rendered the requested interface unusable. In the spirit of the customer is always right, researchers proved the warfighter ultimately wise in their request for a novel large area display human-machine interface by testing a head tracking algorithm called Rhino Pointing, alongside eye tracking. Rhino Pointing was simpler to implement and offered improved accuracy and decreased task completion times. Though not as effortless as eye tracking from a physical workload standpoint, evaluation of the Rhino Pointing concept during flight tests demonstrated significant improvements over traditional touchscreen large area display human-machine interfaces and offered the warfighter a superior alternative to eye tracking in most measures of performance. Researchers experimented in a tactical live flight environment with fifth-generation fighter operationally represented flight helmet to determine if eye tracking as a combat large area display human-machine interface could meet warfighter needs. A head tracking algorithm called Rhino Pointing was specifically added to the research because the warfighter requested eye tracking human machine interface was assessed at a NASA technological readiness level of 4 and was hypothesized to be marginally successful as a combat aviation human machine interface at best. Subjects used 3 human machine interfaces to execute 3 tasks. These tasks were executed across 5 environments on board an L-29 aircraft while seated at the rear seat crew station while wearing an instrumented, operationally representative flight helmet. Method: participants and apparatus. 5 expert United States Air Force fighter aircrew called evaluation pilots who had at least 1,000 hours of fighter time as well as experience in the last 5 years with air-to-air intercept were selected for this paper from a large data set. All evaluation pilots had experience with the control human-machine interface, hands-on stick and throttle and touchscreen, which was implemented in the aircraft in similar fashion to fifth-generation fighter aircraft. None of the participants had experience with the 2 interventions, eye tracking nor Rhino Pointing. The researchers used an Aerovoto Chodi L-29 aircraft for this research. The L-29 was operated in the experimental research and development category and was fully aerobatic and capable of performing high dynamic maneuvers up to 7.5 Gs positive or negative 3.5 Gs at speeds up to Mach 0.7. This L-29 was highly instrumented and used state-of-the-art avionics that incorporated onboard and net-centric air warfare simulation capabilities, weapon models, fire control radar simulation, and helmet-mounted display capabilities. The operationally representative flight helmet used in the study was a fifth-generation fighter aircrew representative helmet-mounted display integrated into the L-29 with a head-track graphics processor. While wearing the helmet-mounted display, the evaluation pilot experienced realistic instrument meteorological condition flying scenarios while operating the L-29 aircraft from the rear seat crew station as if they were in a single-seat fifth-generation helmet-mounted display fighter environment. Intervention. The eye tracking subsystem consisted of a decawless professional eye tracker integrated into the operationally representative flight helmet. 2 eye cameras were mounted directly onto the helmet visor in front of and slightly below the eyes of the evaluation pilot. A scene camera was mounted facing outward on the front of the oxygen mask. The eye camera used infrared video to track the pupil of the wearer. The eye tracking algorithm assumed that a vector orthogonal to the surface of the eye at the pupil indicated the instantaneous user gaze location. The Rhino pointing subsystem consisted of a Paul Hamas Scout head tracker integrated into the evaluation pilot station and operationally representative flight helmet. 3 orthogonal alternating current-powered electromagnetic coils were mounted in the rear cockpit, and a small magnetic receiver was mounted onto the operationally representative flight helmet. The head tracker measured variations in the local electromagnetic field due to helmet motion to determine the 6 degrees of freedom, position, and orientation of the operationally representative flight helmet. The system used pre-flight calibration offsets to define a vector known as the Rhino bore sight, rigidly affixed to the helmet, which indicated the location of interest of the evaluation pilot on the display, as if a rhino horn was protruding from the head of the evaluation pilot and touching the lower display at a point of interest. Tasks and maneuvers. 2 tasks across 6 maneuvers were flown. First task was a slew control cursor, eye tracking cursor, or Rhino pointing cursor to a track as quickly and as accurately as possible as soon as it appeared. Once the cursor was slewed, a hands-on stick and throttle button was used to designate the track for all human-machine interfaces. The second task was to use touchscreen, eye tracking, or Rhino pointing to enter a predefined alphanumeric text string using an on-screen keyboard. The first maneuver was deemed baseline and consisted of the evaluation pilot flying straight and level while executing the 2 tasks. Second maneuver was deemed low workload and required the evaluation pod to maintain 30 degrees angle bank, level altitude, and a constant airspeed while executing all tasks across all human-machine interfaces. Third maneuver was deemed high workload and required the evaluation pod to maintain a 3 degree per second turn rate while climbing or descending at 500 feet per minute at a constant airspeed while executing all tasks across all human-machine interfaces. The next maneuvers were flown by the safety pilot in the front seat while the evaluation pilot executed the tasks while not flying the aircraft. The fourth maneuver was a safety pilot flown 2G normal load factor turn, flown while the evaluation pilot executed all tasks across all human-machine interfaces. Fifth maneuver was the same except at 3.5 Gs. The final maneuver was deemed the operation-relevant air-to-air intercept maneuver. During this maneuver, multiple air-to-air adversaries appeared on the screen. The evaluation pilot was responsible for using the run human-machine interface to designate each track as quickly and as accurately as possible, then to assign a distance-appropriate weapon to that target, all while flying the aircraft safely, meaning that no specific altitude or airspeed tolerances were assigned. Dependent measures. There were 5 dependent measures. The first dependent measure was time to an initial action in response to a track. This was defined as the amount of time from track appearance until a hands-on, stick and throttle, eye tracking, or rhino pointing cursor was flew to the track. The second dependent measure was the amount of time taken to enter a predefined alphanumeric data string using each human-machine interface. The third dependent measure was the track first action distance error, which was defined as the distance the cursor was from the track when the evaluation pilot designated it with the hands-on, stick and throttle, or the distance from the track where the eye tracking or rhino pointing cursor was slewed before designation, since designation was always accomplished with a hands-on, stick and throttle action. Electrocardiogram data was obtained from the evaluation pilots through the flight and used to calculate objective real-time mental workload as a fourth measure. The electrocardiogram time series data was transformed into phase space using the cognitive assessment toolset software. This step established the ergodicity transition matrix that represented the dynamics of the electrocardiogram signal in phase space for the different conditions in the flight. The transitions within ergodicity transition matrices were summarized into a single metric termed the transition probability variance. Transition probability variance calculated the variance of the probabilities of transition from one cell to another different cell of the coarse-grained ergodicity transition matrix. The transition probability variance therefore captured the variability in the dynamics of the electrocardiogram signal as the evaluation pilot underwent different levels of cognitive loading. Transition probability variance varied inversely to the degree of workload, with higher transition probability variances numbers seen under low workload conditions and low transition probability variance numbers seen under high workload conditions. Transition probability variance-based workload was calculated continuously for the evaluation pilot throughout each flight. Finally, as a fifth measure, the evaluation pilot filled out post-flight questionnaires using a 6-point subjective rating scale, with 6 being very satisfactory, to evaluate user satisfaction with human-machine interfaces. All results, other than subjective satisfaction, were presented using box plots where large dots were means, solid horizontal lines were medians, vertical lines were quartile boundaries, and small dots were outlier quartile data. Test statistics were produced by Wilcoxon tests. Test statistics for 1 star indicate a p-value of less than or equal to 0.05. 2 stars indicate a p-value less than or equal to 0.01. 3 stars indicates a p-value less than or equal to 0.001. And 4 stars equals a p-value less than or equal to 0.0001. Results of discussion. The first data product is time to initial action in response to a track versus human-machine interface by maneuver. The control human-machine interface suffered from very long times to slew the cursor across the large area display, which is what drove this research into eye tracking and rhino pointing. While eye tracking and rhino pointing were always better than control, they only differed from each other in the 3.5 G maneuver, where rhino pointing far outperformed eye tracking due to G-force-induced eye tracker slippage. The second data product is time to enter alphanumeric data versus human-machine interface by maneuver. The control outperformed both eye tracking and rhino pointing in time to enter alphanumeric data due to the use of touchscreen over hands-on, stick, and throttle. Of note, rhino pointing was always better than eye tracking, so statistically significant amounts in 3 of 5 maneuvers. The third data product is track versus action distance error versus human-machine interface by maneuver. The control was always the most accurate. However, rhino pointing matched control accuracy in the baseline maneuver and was typically only about 1 centimeter further from the target than the control. In contrast, eye tracking suffered unsatisfactory accuracies across all maneuvers. At elevated G-forces, eye tracking was unusable for selecting a specific track. The fourth data product is objective mental workload versus human-machine interface by maneuver with the evaluation pilot flying. Objective mental workload was always increased for eye tracking over the control across all 3 workload scored maneuvers. Of note, rhino pointing did not increase workload over the control, except for the tactical maneuver. Eye tracking always increased workload over rhino pointing. Of note, workload without reference to performance has little utility. Flight technical performance was calculated. However, no statistically significant differences were noted between human-machine interfaces, so they were omitted here for brevity. The fifth and final data product is subjective human-machine interface satisfaction. Comfort using rhino pointing was found to be lower than control, but not statistically worse than eye tracking. An investigation into subjective feedback found that evaluation pilots were experiencing an increase in physical workload in the form of neck strain to use rhino pointing at the edge of the display. Finally, overall usability of eye tracking and rhino pointing were found to be lower than the control. However, rhino pointing was found to be statistically superior to eye tracking. Conclusion. While the control performed better when it came to accuracy and some measures of satisfaction, the control showed the limitations of the hands-on, stick, and throttle use with a large area display. The warfighter desired to overcome these limitations with eye tracking. Results also showed that while eye tracking felt effortless at times from a physiological and mental workload standpoint, eye tracking performance degraded with time and failed under operationally representative G loadings. While rhino pointing did not offer the low physical workload in some environments that eye tracking sometimes offered, rhino pointing did consistently offer better fighter aircrew performance across all environments. This research showed that eye tracking suffered from unacceptable accuracy and mental workload increases with no flight technical performance changes. The warfighter customer was correct in that the large area display human-machine interface problem needed to be solved. Rhino pointing, while not as accurate as the control, offered almost all the desired eye tracking performance while only incurring a small physical workload penalty. Given that Rhino pointing was less costly and simpler to implement than eye tracking, it is an ideal candidate for implementation in the fifth generation tactical aircraft until eye tracking makes for a higher technological readiness level. Without the customer's always right mentality, this research would have found eye tracking abandoned as of 2021 combat aviation human-machine interface. Instead, researcher foresight and desire to prove the combat aviator ultimately correct ensured the warfighter found a satisfactory alternative large area display human-machine interface in Rhino pointing. Thank you.